Welcome back. So we're going to go a little bit further in looking at the sketch of derivatives from original function, and I'm going to try something a little bit experimental today. I'm going to invite my son to come and join us, and I'm going to see if I can teach him some of the basics of sketching the derivatives. Now remember, my son is quite young, and we're just wanting him to be able to find the turning point of derivatives. And then I'm going to discuss other factors that we want to consider. So, Owen, do you want to say hello to everyone?
Hi.
Okay. So let's start by having a look at a function. So we have this is what we call a set of axes, Owen. This is called x. This is called y. So x goes side to side, y goes up and down, yeah? And then we're going to put some function, okay, that looks like that, okay? And this function, we can give it a name. We might call it fx, okay? And what we want to do, or what we want to be able to do, is we want to be able to sketch the derivative of fx, okay? And in terms of y, we call that dy dx. And these x values still hold. Now, what I want you to be able to understand today is how to find the turning point.
Okay.
So what I'm going to do here is I'm going to say, look, so if you could imagine this green curve, and imagine I had a straight ruler, yeah? So imagine that. And let's say that I put this ruler up against it, and it looked like that, yeah? And then I had another point, and I put it like that, and I had another point, and I put it like that. You can see that. And I had another point that looked like that. Can you tell me, what do you think the ruler is doing at this point? What do you think?
It's getting steeper and steeper.
Well, it's getting steeper. Okay, it gets steeper as I go this way, but at this point, the ruler is going to be flat. Okay, and this is what we call our turning point, or we've got another point which we call a point of inflection. And we can see here, do you think the ruler is getting steeper and steeper as I go along in that direction?
Yeah.
Yep, good. All right. Now, what I want you to focus on is this turning point, yeah? So this turning point is when we have the ruler and it's flat, okay? So it's flat against the ground. If we think of x being down at the ground, yeah, it would be flat level with the ground. Not on the ground, but, you know, flat level with it. And what we want to do is we want to take this turning point and we want to put a line going straight down. This is why we straight down for this x. So this could be x equals a, don't worry about that, Owen. But what we're wanting to do is to put our graphs in sync with one another so that they can see it. And then what we're going to do is we're going to say that our turning point, okay, at this x equals a point is flat. It means it's 0. Therefore, on the graph dy dx, that is 0, and that means that it's an x-intercept. Now, we also know here that these are negative, and here they're positive. And they're getting steeper and steeper. So for this one, for example, could be, it's going to be negative, but it's a large negative. And we keep on going through until we get points like that, okay? And that gives us a basic expression of our derivative function fx. So what we're going to try to do, Owen, is I'm going to give you another graph now, okay? And what I'm going to ask you to do is be able to find the turning point. So this graph is going to look like that. Okay. and we're going to say that that's y and x. We're going to line these graphs up, and I'm going to hand the pencil over to you, Owen, so that you can tell me where you think the turning points are. Okay, so here you go. Tell me what you think. Hold it here. Okay, where do you think the turning points are going to be? Okay. Okay, maybe not quite there. Okay, close, but the turning point you have to be really, really accurate with this. Turning point's going to be there, yeah? Where else do you think the graph is flat? Okay, where you think it's flat?
Here.
Okay, yeah, good. Here. Very good. So we can see here that our derivatives are 0. Okay, and how that translates to our graph of our derivative function, it means that we have 0 points at that point. Okay, so 2 0 points. Now what we might also have a look at is what are the gradients at these certain points here. Well, we can see that at this point the gradients are positive. At this point here, if I consider these gradients, they're positive as well. And then at this point, they're negative. So this is going to be a little bit strange with our graph, because our graph, I'll just put it in the right colour, our graph is going to look something that looks like that. Okay, where we have positive gradients going here, still remains positive, but sort of switches up, and then goes into a negative range. All right, thanks, Owen. Do you think you've got some of it? You think you can at least identify turning points?
Yeah.
All right, good. So here we have got two problems. Thank you, Owen. I'll see you later. Here we have two problems where we're being asked to sketch the derivative function. So what I'm going to do for these problems is I'm going to set my axes up, and then I'm going to orientate it in terms of what's happening here. Well, obviously I've got a turning point here, and I've got a point of inflection here as well. Okay, so what that means is if I bring these down, that means they're the 0 points or x-intercepts for my derivative function. Now I also want to explore what's happening with this graph. So at this point here, okay, we have negative gradients. In between here and moving on here, we have positive and positive. So therefore I can start by saying, well, this is steep negative, steep getting down to 0, okay, going up, but then it sort of flattens out a bit to 0, and then it starts getting steep again. And this is what my f dash x would be. In this example, this next example, f, this is a little bit strange because what we have is we have an asymptote. So here we have my asymptote. Okay, and we haven't really discussed how we deal with asymptotes in this slide. Well, if we think that the asymptote is when the graph doesn't pass it, okay, or the graph is approaching affinity, when I think about this graph as it moves up towards the asymptote the steepness of the graph is getting increasingly large, and so large that when it really approaches the asymptote, it's approaching infinity. Therefore, we keep the asymptote where it is when we're sketching dy dx. Okay? And then we're going to have a look at all other components from here. Well, we've got a turning point at here. Okay, that means 0 point. Either side we have positive gradient increasing. So we can draw that section of the graph quite easily. In this section of the graph, what we have, not positive, but we have negative gradients. And those negative gradients are flattening out to 0. So as it approaches this y equals 3, the graph is getting closer to 0. So what we have is we're going to have some aspect of a graph that looks like that. It's still negative, okay, because the gradients are all negative. But remember, as I go towards, so x approaching negative infinity, dy dx approaches 0. And that's what I'm trying to show with my graph here. You know, as it gets close, it's getting closer to the x-axis. All right, thank you. I hope the video helps.